Welcome to this video on sampling. In this video, we are going to continue our discussion of sampling and talk about the so-called impulse train or comb. Whenever we have a continuous time signal, we have to record the values at certain points. Let's call this x of t. The issue with calling the sampled version of x of t as just this, excess of t is actually x of t. Let's say that this is actually, we are sampling at regular intervals. This is nt, n plus 1t, and so on. When t is equal to nt and 0 otherwise. The problem with this approach is that the resulting signal excess of t can be shown to be a so-called zero energy signal. Of course, you may argue that it has all the information about excess and x of t and all those things, but since you are essentially storing non-zero values for x of t at just a countable number of locations, it becomes a zero energy signal and complicates the analysis, in particular using the Fourier transform for further processing. The details of this are beyond the scope of this class, but you can look at some material on real analysis to understand why this kind of function construction is not preferred. So what do we do instead? As you may have seen in signals and systems, we use the helper function, the so-called impulse train, which uses several delta functions in series and so on at regular intervals. Okay, and these are at k minus 1t, kt, k plus 1t, and so on. And we call this, let's call this s of t for the impulse train. Now this impulse train has a slight advantage over this direct approach which we took in the previous case. What does x of t multiplied by s of t look like? Well, let's look at this x of t. Let's bring it over here. Okay, and let's get rid of this. So what does it look like? Well, if we're going to represent it using a red color, then the way it looks like is this. It looks like an impulse over here, an impulse over here, an impulse over here, an impulse over here. So it's a sequence of impulses at every integer multiples of t, and the weight of those impulses is exactly x of t at those particular points. In between, it is 0. It's actually 0 in between. Now, you may argue, what is the major difference between this and what you showed earlier? In the earlier case, you just put the values over here, while in this case, let's call this original xs prime and then let's call this my actual xs. My xs of t is x of t multiplied by the impulse train. The formula for the impulse train is just a sequence of impulses spaced t apart. N is minus infinity, delta of t minus nt, and if you bring this inside, it becomes summation n runs from minus infinity to infinity. If you multiply x of t by the impulse which is centered at nt, you will end up getting x of nt. What have we gained by taking this approach? The key benefit is that if you look at one of these impulses, the area under the impulse represents the value of the signal, and the signal itself doesn't, its energy is undefined to be very particular, but it's not one of those zero energy signals. Of course, this does not come without its own set of problems. The primary one being that the impulse is not exactly a valid mathematical function. If you look at analysis, they will tell you how to handle this. But for us engineers, this is a better way to represent it, because then the complete Fourier transform machinery becomes available to us. How? If you look at the impulse train can be represented, as I mentioned, as a series of impulses. The continuous time Fourier transform of these impulse train is surprisingly another impulse train. The only issue is that it is separated at 1 by t. So in other words, if you have an impulse train which is spaced t apart in the time domain, then it is spaced 1 by t apart in the frequency domain. What is the implication of this? If you look at this example will make it clear. If you space the impulse further and further out in the time domain, it becomes closer and closer in the frequency domain. Similarly, if you space it closer in the time domain, the impulses go further and further spread in the frequency domain. This has a direct connection with the aspect of sampling, because if you now look at what sampling is, if we define it as multiplication with an impulse train, in the frequency domain, remember that multiplication corresponds to convolution. This convolution of x of f with s of f is going to directly have a bearing with regard to the utility of sampling. This is something we will see in a subsequent video. Thank you.